Welcome back to Twisty Puzzle Math. This is the 6th video, and I want to discuss conjugates. So previously we discussed commutators as a way of generating some moves for the cube to find ways of permuting the edges or permuting or twisting the corners. So let's use an example. So the Z commutator, which is F commutator R, it looks like a Z because those are the pieces that are affected. So this is all right. So maybe useful, but you might object that it's affected too much of the cube. When would you ever need a move that affected this much of the cube? You might want a move which only affected one layer of the cube, and this certainly is not doing the job. So how can we change this? So here's what a conjugate is. If you have a move, say P and Q, a conjugate might look something like this. There are a couple ways of doing it. It could be P, Q, P inverse. So Q might be a desired move like our commutator. It does something nice, but not quite the way we want it to. And P is a process to improve, if you will. And I'll demonstrate what I mean in a minute. So we might do something to the cube so that Q is more beneficial to us. And then P inverse undoes P. So what does that mean? That's kind of confusing, perhaps. So our Z commutator affected a whole bunch of the cube. How could we confine it to one level? Well, here's a way. So suppose I were to move, I do a D, if you will, right? Now, the Z commutator will affect this part of the cube, but notice that the lower part is actually in the front layer. So what I'm doing is this in notation. I'm doing a D, then I'm doing an F comma R, now I'm doing a D inverse. That's a text message from my oldest daughter who's currently working on the cube remotely and asking for help. So let's work this out. I do a D, then I do my commutator, F, R, F inverse, R inverse, and now I do D inverse. And now the result of the commutator is only on one level, right? Everything is contained in this level. So this is very useful. I'm going to put D back. Remember, if we do the commutator, say twice, well, if I do it again, the corners are back where they belong. And if I do it again, the edges are back where they belong. And I can undo that D. And now what I've got is a move which has swapped a pair of corners in the same layer. So I've generated a move which swaps opposite corners in one layer. It does nothing else to the cube at all. So if you've never solved the cube before, you could imagine that this might be a helpful move. If you've got a lot of the cube solved, you just have a couple corners left, and you're trying to put them in the right spot, here's a way of doing it. And so that's not this move. The move I'm showing you right now, the result, would be D, F, R, the commutator, done 3 times D inverse. And so the conjugate is this process of setting up for your move. The move you discover that you record in your notebook, you do all the cycle notation work on and whatnot, that move might involve a lot of pieces of the cube. But using a conjugate, you can restrict the effect of that move to a certain targeted area of your cube. Let's do another example. back to the identity. So let's see. Here's another example. If I do f squared r squared, and I do it 3 times, this is a move I first saw in Singmaster's little notes on the magic cube. What it does, it takes these 2 edges and it swaps them with these 2. So that's potentially neat. So up front goes to down front, and up right goes to down right. It's a pair of edge swaps. But again, just like the Z commutator, this might not be desirable. You may not want this kind of motion. You may want something confined to a layer. Maybe not. It depends on what you're doing. So how could we improve this move to affect only one layer? Suppose we wanted to swap opposite edges in a single layer of the cube. Maybe what I want is up front, down front, and I want front left, front right. That's the desired. That's the goal. These 2 swapped and these 2 swapped. Here's one thing you could do. So you could twist these 2, so that would be a U prime, or U inverse, and a D, all right? So they're on the right-hand side. Now I could do an F prime, and now I'm in a position where if I do the F squared R squared, 3 times, it'll swap these pieces and these pieces. Let's try it out. So F squared R squared, F squared R squared, F squared R squared, right? So I'm going to write that down. Whoops. And then reverse these moves, which would be an F, a D prime, and a U. So there's my F, there's my D prime, and there's my U. Now the result is that the up front has been switched with the down front, right? And also the front left has been switched with the front right. So using a conjugate, right, sandwiching this move between these 2 has allowed me to create a process whereby I switch opposite edges. All right. Now, from what I've read, back in the early days of the cube, these processes that people had for solving the cube were very, very long and very, very cumbersome. So much so that people weren't solving the cube by memory at first. They had to have a sheet of notes next to them. One of the first people to do it without notes, what I've read, is John Horton Conway, who's particularly well-known and brilliant mathematician in England. So it's not surprising. But I've also heard that people who were solving the cube might see someone in public, on a bench, or in a bus working on it, and you might go up to them and ask them for some of their processes. You know, do you have a 3-cycle for edges? Do you have a way of twisting corners? Do you have a way of doing this thing? And you might trade moves. Maybe your process for doing this is very long and cumbersome. This is a lot of different moves. Maybe they have a shorter version, which is more efficient, and so people would trade these. It's also possible, maybe I'll try to put a link for this, but the early Usenet cube group is kind of fun to read because it has people posting their algorithms, posting their moves. In fact, I don't want to run out of time in this video, but one of the things that's in here a lot, the notes on the magic cube, are lots of different algorithms. I don't know if you can see that. And also there are some cycle notation things for twisting, for using one layer, flipping things. These were very, very valuable to have. And because some of these moves you discover by accident. You know, you start with commutators and conjugates, but sometimes you just do something and see what happens, and you find a particularly elegant move. But I don't want to overrun my 10-minute limit, so I'm going to stop the video right here.